Hey guys, I think I'm going to get started. It's 12:30 here. I'm Rachel. Thank you for coming to my talk about strings and emoji and Unicode. The slides are at the bottom there if you would like to follow along. A little bit about me. I'm currently an iOS engineer at Venmo, an app for sending money to friends and family. On the side, I'm working on a project called Untitled Chapter, which is an app to help maximize fun and learning for readers of print books. So if you can't tell from the last few slides, I love emoji. This is probably one of my favorite ones. I just find them to be really expressive and to just do so much that words can't do. On emoji, the laughing, crying emoji was even voted Oxford English Dictionary's Word of the Year in 2015. So I just found that I was starting to have this curiosity around emoji and the code underlying them. And this is hinted at by the fact that emoji look different on different platforms. So if I send this thinking person emoji to a friend with an Android, it's going to be rendered differently. And I just sort of wondered why that was. So when we talk about emoji, we have to talk about strings. An emoji is a type of string. The sentence itself is a string. Okay, great. So what's a string? A string is essentially an ordered collection of characters. And when we start talking about collections of characters, particularly when it comes to computers, we have to talk about something called encoding. So encoding is essentially a structured way of representing and storing those characters in a string. I have some examples of encoding systems here, starting with non-digital systems. So an example of an encoding system is actually Morse code. People are probably familiar with this. Essentially, you use a series of dots and dashes to represent different letters in the English alphabet. I discovered that there are actually different versions of Morse code for languages with non-Latin alphabets, which is fascinating. Another version of an encoding system is the American Sign Language finger signing alphabet. This is where you hold your hand in different configurations to represent letters of the English alphabet. So then we start getting into more digital systems of representing text. We've all probably heard of ASCII. It stands for American Standard Code for Information Interchange, and it dates all the way back to 1963, so sort of pre the internet as we know it today. The way that ASCII works is it assigns the letters in the English alphabet, some punctuation, and some control characters, a number from 0 to 127. And it's actually right in the name American Standard Code for Information Interchange. So this sort of hints at a problem we're going to run into with this system of encoding. So say we're storing data on disk. We have a sequence of bytes here. If we use ASCII to interpret this sequence of bytes, we have a sentence that we can all parse and that makes sense. But if we use a different system of encoding, we might get letters in a different alphabet, different language entirely. These do not actually translate to the same thing, I checked. So ASCII was great sort of at the dawn of the internet when we were just dealing with English. But as we all know, we live in a global world. We have a lot of people that speak non-English languages or languages that don't have Latin alphabets. So that's where Unicode kind of came in. Unicode was created because there were all these different encoding systems that cropped up to deal with what ASCII couldn't deal with because it only dealt with the Latin alphabet. So it's overseen by the Unicode Consortium, which is a collection of individuals and businesses that are sort of invested in the problem that Unicode is solving. And it covers 150 writing systems, which is quite a few. I highly suggest checking the website out. There was a piece of news from a year or two ago that talked about funding for Unicode Code Points and Mayan hieroglyphs, which is really interesting. And in the background of the slide here is actually the mapping of Unicode Code Points to Egyptian hieroglyphs. So it covers languages that are very dead and very alive. In Unicode's own words, they provide a unique number for every character, regardless of what the platform, program, or language is. So it's sort of directly attacking this problem where you might be on a different platform and a character could show up a different way because it's using a different encoding. Unicode wants to sort of cover all that ground. So delving into some of these terms a little bit, there's a lot going on here. So if you were at Stump 360 last night, you'll already know that there are over 1 million Unicode code points. So we gotta define code point. First of all, a code point is essentially a hexadecimal number. So the hexadecimal system is a base 16 system of counting. It's represented by U for Unicode plus a sequence of numbers or letters and numbers. And so a code point is an individual representation of a character, essentially. The whole range of Unicode numbers is divided up into areas called planes. We have the basic multilingual plane, which we'll look at in a sec. We have these other planes called astroplanes, which is a really cool name. We have private use, which we are definitely going to come back to. And right now we are on Unicode 12.1, and there are 137,000 characters or code points defined in Unicode. So delving into the basic multilingual plane a little bit, we have a whole area devoted to various alphabets. We have an even larger section for Han characters, which was something created to sort of unify characters from Chinese, Japanese, and Korean. We have a small section for Yi, which is Chinese ethnic language. We have Hangul, which is a Korean writing system. And then we also have a private use, which we will get back to. So some of the various writing systems covered by Unicode, I just have some examples here. So we have various African scripts, including the Egyptian hieroglyphs. We have Central Asian scripts, and we even have scripts for Indonesia and Oceania. So it really covers a lot of ground. So this here, there's two things I really want to point out. First, you notice sort of the precipitous growth right around the turn of the century where Unicode is really picking up speed. The world is globalizing, so it sort of makes sense. And this graph also shows the comparison of emoji to non-emoji Unicode code points. So we all have emoji, it's probably why a lot of us are here, but it really makes up a very small portion. Most of it is for like writing systems in various languages and such. So bringing it back to emoji, this thinking emoji is just a code point under the hood. So the code point is listed up at top, and it's essentially up to the platforms and the various social networks to decide how to render this emoji, so this code point. So Unicode has dictated that U+1F914 is named the thinking face emoji, but the platforms basically get to decide how that shows up. So Emojipedia is a really great resource if you're curious to see kind of how goofy emoji look on non-Apple platforms. Maybe I'm just used to Apple, but yeah. So maybe you've heard UTF-8 before, you've heard of UTF-16, maybe UTF-32. What is it? So UTF, first of all, stands for Unicode Transformation Format. And these are systems of encoding. So again, they are contracts for how to structure, represent, and store text. Specifically, they talk about how to map between code points and bytes. So remember, we're dealing with computers, everything is sort of bytes at the end of the day. So there are a bunch of differences between these two encoding systems. UTF-8 uses minimum 1 byte per character, whereas UTF-16 uses minimum 2 per character. There are various trade-offs to using one versus the other. For example, for non-European languages, UTF-8 actually requires more memory than UTF-16. So if we take this thinking emoji, and we print out the data underlying this string, first using UTF-8, we get a sequence of bytes. It's 4 bytes long. If we then print out the sequence using UTF-16, we get an entirely different sequence that is actually 6 bytes long. So there's certain ways in which you can't really compare UTF-8 to UTF-16 or different encoding systems. They're basically non-compatible. So that brings me to this quote from Joel Spolsky, who is the founder of Stack Overflow. I hope if you take one thing from this presentation, it is this quote. So Joel Spolsky says, "It does not make sense to have a string without knowing what encoding it uses." I think as iOS and Swift developers, we have a certain level of abstraction, and we tend to think we're dealing with like pure types. Like string is just a string. You don't have to think about it too much. But as a matter of fact, encoding, as I said, is basically the contract for how that text is represented and stored. So it turns out encoding is actually really, really important. We see this come into play in the differences between Swift 3 and Swift 4. So again, with the thinking emoji, in Swift 3 and Swift 4, it's one character count long. That's as you would expect. But when we start doing more complex things, so if we use an emoji with a skin tone modifier, or if we use the family emoji, which I'm sort of calling compound emoji. So the family emoji is essentially man plus woman plus boy plus girl, all joined together by these characters called zero-width joiners. They're sort of the glue that connects these disparate code points together. So in Swift 3, we can see with these more complex cases, we get kind of weird results. We get a character count of 2 or 4. Swift 4 kind of straightens it out. All these look like one emoji, and you indeed get a character count of 1 in Swift 4. So like if you're Twitter, this might really matter. You might want to actually know how long a string is. And the reason that this situation was produced was Swift 3 was using a certain version of the Unicode standard, and then Swift 4 switched to a different version. So this sort of brings me back to my point that the system of encoding you're using really matters. So that brings me to custom emoji. If you use Slack, you're probably pretty familiar with typing in a word surrounded by colons to put an emoji in. This is one of my favorite custom emoji. It's sunglasses plus crying. We call it soft glasses. We also use a bunch of custom emoji in Venmo, which is where I sort of got the idea for this talk. And I mentioned earlier that we were going to come back to Unicode private use areas. So they're exactly what they sound like. They are blocks of the range of Unicode hexadecimal numbers or code points that Unicode has basically reserved for consumers to define themselves. And Unicode has guaranteed that they're not going to plop an emoji or another character down in these private use areas. You can basically do whatever you want with them. So these private use areas are the key, really, to doing custom emoji in your own app. So there's a couple of different steps here, and it starts with mapping a human-readable string to a code point that's in one of those private use areas. So you're going to want to create a JSON that looks a little like this. On the left, you have a human-readable string. I've surrounded it by colons because that seems to be kind of the publicly accepted way of denotating emoji now, but it's totally arbitrary. You can put whatever you wanted there. You can put a comma. You can put nothing at all. On the right, this is a Swift string, essentially. So we have the escaped U, which indicates a Unicode scalar. For the purposes of this talk, you can think of a scalar as basically a code point. And then we have E000, which is the hexadecimal number that indicates where in the range of numbers we are. So there's a ton of resources online. I've listed one up there where you can plug in a character and it will tell you what it's called and what sort of block it lives in. So plugged in U plus E000, and it doesn't have a name as we would expect. Confirm that it is a private use character and it lives in one of our private use areas. So once you have that JSON, the next thing you want to do is generate a custom font. So there's this guy named Bedad Esfabad. He works at Facebook now. He has a repo, public repo, with a script in Python that takes in a JSON, pretty much like the one I just showed, and it takes a set of images and it embeds those images in an existing font file. So this script basically does all the heavy lifting of connecting the human readable string to the code point to the images. And the output of this script is a .ttf file. If you've ever used a custom font in your app, you're probably pretty familiar with these. You can just load it up to the font book on your Mac. This is the Venmo custom emoji font with a couple examples. And the result is a UI font. So you can use it the way you would use any custom UI font. And that crucially includes changing the size of the font. So that brings me to step 3, which is profit. You can get emoji that are big, bigger, and biggest. It's kind of a goof. You can make your emoji as big or as small as you want. But we've all probably seen Apple's, like what I call megamoji. So if you type up to 3 emoji in an iMessage, they will be big. But if you type characters, or if you do more than 3 emoji, they will get smaller. And what I really want to emphasize, this is a little speculation because I don't know how Apple is doing things under the hood, but if I had to hazard a guess, I would say that it's probably pretty similar to what I just talked about, where it's a UI font, and the size of those big emoji and the number at which they get bigger or smaller is totally arbitrary. It's probably a constant somewhere. So you can sort of take these foundational ideas and put them into your own app for the biggest emoji. So we've all probably seen the question mark in a box that shows up. Maybe your friend with an Android gets the newest set of emojis before you do, and hopefully you understand a little more why that might show up now. So it's all code points under the hood, and your system just doesn't know how to interpret this new code point. It doesn't have the new OS, so it sort of falls back to this weird representation. It kind of looks like a Mario box or something. I've also seen an alien in a box. But hopefully you can now move away from that and move into the wealth of emoji that exists out there. So to summarize, we talked about systems of encoding. We defined encoding as a structured way to represent and store text. We talked about some specific examples of encoding, like Morse code and ASL and ASCII, and then we specifically talked about the Unicode system of encoding, which was meant to unify all these disparate systems. We talked about code planes, which are blocks within the range of Unicode numbers, and we talked about code points, which are individual sections inside of those code planes that represent certain characters. And then finally, we talked about custom emoji and using essentially a font to add custom emoji to your app and make them as big or as small as you want. So that's it. Thank you.